And tell me, which number and its conjugate is the same?
Real number.
For near number. And x and x must be real. Clearly, from 2 and 3 we can get this, that alpha x1 plus beta x2 and y is alpha conjugate x1 y plus beta conjugate x2 y. And in general, the inner product, the complex including inner product for of x and y belonging to Cn is, the formula was, do you remember what was the formula? It was x permutation y, whereas in the real format we had x transpose y. What about this one? What can we say about this? X y Hermitian.
Again, rank.
Again, rank 1. This is again a rank 1. This is again a rank 1 matrix. X Hermitian y should be always real, or can we have any comment, or should be always complex actually?
In general, complex.
In general, no comment, because if x and y are real, both of them are real, that means that they are also in C, which the result by default is real. X can be complex, y can be real, so the result is in complex. X can be complex, y can be complex, the result can be in complex. X can be complex, y can be complex, the result can be real. So we cannot comment. We cannot comment. But the result is definitely in C. The result is definitely in C. Now, as we have the complex inner product, and we have seen the Euclidean inner product in the complex form, let's look at what will happen if we have a weighted inner product in C. And x1y over q is x Hermitian qy for arbitrary q equal to qh as positive definite. So q is equal to qh. Do you remember what it's called? It's called a Hermitian. It's Hermitian. Q equal to Q transpose was symmetric. Q equal to Q Hermitian. It's Hermitian. What else can we say about Q? What can we say about elements on its main diagonal?
Real.
They must be real, because in both of them they are the same, and only real numbers conjugates are the same as each other. Vector space of V over field F endowed with a specific inner product is called an inner product space. If the field is complex numbers, we call V a complex inner product. If F is R, we call V a real inner product space. Here I missed the word space also.
Question. A vector space by definition has an inner product, but basically it's not an inner product space unless, wait. Doesn't the vector space by definition have an inner product?
You tell me, does it? It has to be closed for multiplication, and a scalar. It has to be closed for addition and a scalar multiplication.
Okay.
Now, three important notes, a kind of reminder, maybe you have seen them before, if not, you see it now. Note 1. Inner product of A and B is the trace of A transpose B. We understand here the vector space is R n by n. Note 2, the trace of A transpose B is the trace of B transpose A is the trace of A. B transpose is a trace of BA transpose. You remember what is a trace, right? It's the sum of all the elements on the diagonal. Node 3, this is a trace of a Hermitian B if our vector space is actually C. Anyway. Let V be a vector space, be an inner product space. Then for V belonging to V, we define norm or length of V by S square root of inner product of V by V. And we know that this is also called Euclidean norm, right? This is called norm induced by inner product. In general, this norm can be actually written as these two forms based on if V is in R or in C. If V belongs to Rn, then norm of V is S square root of summation over I of Vi square. And if V is in C, norm of V is the summation over I of magnitude of V squared. And we have a theorem which is known for us, we knew it before even. Let P be an orthogonal projection on an inner product space V. Then norm of PV is less than equal than norm of V for any V belonging to vector inner product space V. When do we have the equality? Do you know when we have the equality? Laura, when do we have the equality?
When the where is the what defines what is projected on? Basically, when they are parallel.
W, whatever.
Okay. When they are parallel.
No,
V
when
and
they are in
W.
the same direction.
Yeah.
When they are in the same direction, like the W space, the vector space that you have, and your V are in the same direction, right? Then the equality holds. Otherwise, inequality holds. The last theorem that today we talk, which we only use the results, is called polarization identity. And it is for x and y belonging to Rn. The inner product of x and y is x transpose y, which is norm of x plus y square minus norm of x minus y square divided by 4, which is norm of x plus y square minus norm of x minus norm of y, each of them is square, divided by 2. And for x and y belonging to Cn, the inner product of x and y is x Hermitian y, which is 1/4 summation of k from 1 to k of j to power k norm of x plus y plus j to power k x squared, where j is the complex unit. And now we are ready to start to talk about norms. What is a norm? How do we define it? What are the properties? What are the different type of norms? What are the applications and so on? Do we have any question?
Is that for k equals to 1 to what?
Oh, well, n with s is n. Whatever. Yeah. Okay. And that's for today.